Hello, welcome to our 27th lecture in the graduate combinatorics course. Today we'll discuss Kirchhoff Matrix-Tree theorem, which gives a formula for the number of spanning trees of a graph in terms of its Laplacian matrix and its eigenvalues. So let's recall some definitions from the previous lecture. For a matrix M, that is n by n real matrix, we denote by Mij the determinant of the matrix obtained by deleting row I and column j from M. And with this definition in mind, we can define the cofactor matrix of M is the n by n matrix C whose ij entry equals -1 to the power I plus j times this determinant Mij. And as you learn in linear algebra, when you study inverse matrices, there is this matrix called the adjugate matrix of M, which is the transpose of the cofactor matrix. And it has the property that if you multiply a matrix M by its adjugate, these two matrices commute, and their product equals the determinant of the matrix M times the all one matrix. And as a consequence of this result, you get a formula for the inverse of a matrix M as being the adjugate matrix M divided by the determinant, if that determinant is non-zero. Now, the Kirchhoff Matrix-Tree theorem that we would like to prove tree theorem states that if we have a graph with Laplacian matrix L, then the adjugate of this Laplacian matrix will equal the number of spanning trees tau of gamma times the all one matrix. Okay, so this will have various consequences, but this is the first result that we would like to prove, and we'll do it in this lecture. Now, the first thing we want to do is to investigate the adjugate of the Laplacian matrix. And we'll prove this proposition that for any graph gamma with Laplacian matrix L, the adjugate of L is the multiple of the all one matrix. And in the second step, we'll figure out that this multiple is going to be the number of spanning trees. Okay. Well, from the definition of the adjugate matrix, we know that the adjugate of L times L equals L multiplied by the adjugate of L, and equals the determinant of L times the all one matrix. But we proved in a previous lecture that L has 0 as an eigenvalue. So we know that the determinant of L is 0, and therefore L times the adjugate of L will equal the 0 matrix. I'll put 0 n. Okay. Now for our proof, we have two cases. So we'll use this fact that we just stated, but we have case one when gamma is disconnected. So if gamma is disconnected, this means that the number of components, the number of its components, number C, I think we denoted, of its components is at least 2. And remember, one of the results we proved in the previous lecture is that the rank of the Laplacian matrix equals the rank of any incidence matrix. It equals n minus c, and because this c is at least 2, this is at most n minus 2. Okay, so what does it mean? If the rank is at most n minus 2, it means that any submatrix, which is n minus 1 by n minus 1, will have determinant 0. So that implies that basically the cofactor matrix of L is the all 0 matrix, and since the adjugate matrix is the transpose of it, it means that the adjugate matrix is the zero matrix, which is 0 times the all one matrix. So in this case, the adjugate matrix is just 0 times the all one matrix. So this case is clear. Now, in case 2, when gamma is connected, the same argument is not going to work, because in this case, the rank of L is n minus 1. And the rank being n minus 1, it means that there will be some n minus 1 by n minus 1 submatrix of L whose determinant is not 0. So you cannot use the same argument. However, we can use the properties that we wrote above, and we can look at the one that I just put there in the rectangle. We have that L times adjugate of L is the all one matrix, all zero matrix. That implies that every column of the adjugate matrix is an eigenvector of L corresponding to the eigenvalue 0. Well, if you pick any column of adjugate of L, it's clear from this equation that L times that column is going to be 0. Now, it's not so clear why is that column have to be non-zero, but yeah, for now, we'll get to that in a second, that every column will actually be non-zero. So for now, perhaps this one, maybe every column, let's call it U with the vector above it. Instead of writing this, we can rephrase it, satisfies the fact that L times U equals 0, the 0 vector. Okay, let's leave it like that. Now, because L times U is 0, by an argument similar to the one that we did in the previous lecture, where we determined the multiplicity of the 0 eigenvalue of a connected graph being 1, it implies that this column U is a multiple of the all one vector. And yeah, this is from the previous lecture. So what we have that in this adjugate matrix, if we look at this adjugate matrix, if you look at the first column, it's going to be a multiple of the all one vector. So let's just call it alpha 1 times 1. The second column will be alpha 2 times all one vector, and so on, alpha n times the all one vector. So it's something, if you want to write it energy-wise, it's alpha 1 on the first column, alpha 2 second column, all the way to alpha n to the last column. But now, because the matrix L is symmetric, that means that the adjugate of L is symmetric. So think about that. Why would this be true? And because of that, if you see the form of this matrix over here on the right side, it implies that alpha 1 has to equal alpha 2 has to equal alpha n. And therefore, adjugate of L will be just, this is, let's say, alpha, it's going to be alpha times the all one matrix J. Okay. And this alpha cannot be 0 because the matrix has this matrix here, L has rank n minus 1. So we get this formula for the adjugate as alpha, some non-zero element times the all one matrix. Okay. All right. Okay. So now let's prove Kirchhoff theorem. let's prove that this alpha actually equals the number of spanning trees of the graph. So gamma, yeah, graph on vertices. So the statement is that every cofactor of L equals tau of gamma. So basically aggregate of L is tau of gamma. So remember that by this tau of gamma, we denoted the number of spanning trees. So here's the idea of the proof. So we know that the aggregate of L equals something alpha times the O1 matrix. So all these cofactors are equal. So we just have to determine one of them, okay? So now let's pick, so we look at the matrix L. This is a matrix L. And we're just gonna pick a vertex, let's say X, which is at the beginning. And we get rid of row X and column X. And we want to figure out what is the determinant of this L. Let's call it Lx. Okay. So how do we obtain that? Well, we go through the incidence matrix. So we take N, let N be an oriented incidence matrix of gamma. And we know that L equals N times N transpose. Okay, so L, our square matrix, this is L, equals N is usually like a flat matrix like this. So this is N. You have edges on this side and vertices on this side times this is N transpose. You have vertices here and edges here. Okay. So what we're interested in now is we're interested in what happens if we delete here X and X. Okay. So here we want to ignore X here, and the same X would be in this part. So the determinant of this matrix here, we call the determinant of this nx times nx transpose, where nx is the one here minus the first, n minus the row of x, and n transpose x is the same, similar thing. Is n transpose x minus the column of x. Okay. So now, how do we calculate this determinant? And here we use this result from linear algebra, which is called the Binet-Cauchy formula. So you see here the nx matrix. So we have the determinant. So this is a general formula whenever you want to calculate the determinant of some matrix A times a matrix B, such as the product is a square matrix. But in general, A and B may not be square, like in this situation. So you have determinant of nx transpose, nx times nx transpose. So this one is V minus X times E matrix, and this one is E times V minus X matrix. Okay. So like I said, you see in the picture, these matrix NX and X transpose are not squares. So it turns out that the determinant can be expressed as a sum over product of determinants of square matrices. And this is how it works. So in V minus X, we have n minus 1 vertices. Here also n minus 1 vertices. So this matrix over here, it's n minus 1 by n minus 1. Okay. So to calculate it, we have, it's a summation over all subsets of edges. So we think of it as columns. We're picking here some f as subsets of edges of cardinality equal to n minus 1 of determinant of nf times determinant of nf transpose. And by nf is the matrix whose so it's the sub matrix of nx whose rows correspond. You take all the rows of nx, all n minus 1 rows to v minus x, and columns correspond to the edges in f. Okay, you pick n minus 1 edges and you take them here and you take them here as well. So that would be nf and that would be nf transpose. Okay. Now, when we calculate this, so this is Binet-Cauchy formula, which is applied here. And now, when you do this summation, well, what happens? We did in the previous lecture, we looked at this matrix NF, and we saw that NF is invertible. If and only if F induces a spanning tree. Okay, so the set of edges gives us a spanning tree. And now a spanning tree in a graph is essentially determined by its set of edges. So as you look through over all subsets of n minus 1 edges, you know, some of them will give you a spanning tree, some will not, but essentially every spanning tree can be found this way by looking at subsets of n minus 1 edges. Now, when we go through this summation, this matrix NF, what contribution do we get? The only contribution we are going to get is when the determinant of NF is not 0. Now, the determinant of NF is not 0. That's the same thing as NF being invertible. And that's the same thing as F giving us a spanning tree. So whenever we have a spanning tree, this term here is going to be non-zero. But now, what is the value of that term? We also, from a previous lecture, we learned that the determinant of submatrices, square submatrices of the Laplacian matrix, are either 0, 1, or -1. So the determinant of NF being non-zero is actually equivalent to the determinant of NF being plus or -1. Okay, and so that is the same as the determinant of NF times, since the determinant of a matrix and a transpose are the same thing as the product of these determinants is 1. Okay, so these equivalents, this term being equal to 1 is equivalent to F being a spanning tree, tells us that the sum that we have here on the right hand side is going to equal the number of spanning tree of the graph, because you count a 1 for every subset of edges that gives us a spanning tree. Okay. So that's the proof. That's one proof. There are other proofs, but this is one proof of this result. Okay. All right. Now there are other equivalent formulations. So this one, you know, maybe it's not so, we may think, okay, I need to get the Laplacian matrix, delete one row and one column, and then, okay, how you can calculate the determinant, you get something. But are there other formulas? Can we use this in a different way? And so here's a reformulation, okay? It's a reformulation. Here. So we take again at gamma graph on n vertices. Denote by L its Laplacian matrix. Whose eigenvalues, so I want to denote its eigenvalues by some numbers. So its eigenvalues are the following. So we know that 0 is the smallest eigenvalue, so mu1, and then it's less than or equal than mu2, less than or equal than mu(n). Okay. So now we have this formulation for the number of spanning trees of gamma is the following. Tau of gamma is going to equal the determinant of Jn plus L divided by n squared. So that's one formulation. Also as a determinant, but it's also the same thing as the product mu2 all the way to mu(n) divided by n. So the number of spanning trees, so this is a purely combinatorial object, the spanning trees. So this term on the left, it's a combinatorial parameter of the graph, equals the product of the eigenvalues of the Laplacian matrix, which is an algebraic invariant of the graph. All right, so how does the proof go? Well, let's do the first one. So there's some identities that are pretty easy. So for example, Jn squared, if you multiply the matrix by itself, it's n times Jn. If you multiply this all one matrix by itself, you get n times the all one matrix. The other one, because L times the all one vector gives us a zero vector, it means that L times the all one matrix, Jn, is going to give us the all zero matrix. And it turns out that they commute. So Jn times L equals the all one, the all zero matrix. So these are simple properties. And from linear algebra, you know that if you look at the adjugate of a product of two matrices, let's say M times N, let's not use N because we use it for something else. So let's use A times B. That equals the adjugate of B times the adjugate of A. Okay. Now, we can do some multiplication, some identities. So one of them is the following. If you take the matrix Ni minus J, so I'll just write J for Jn and I for In, times J plus L. What do you get? So this is N times J minus J squared plus N times L minus JL. Okay. N times J minus J squared, that's 0n from the first equation. J times L is 0, so we get plus NL minus 0n, so we get N times the Laplacian matrix. Okay, so now if we apply adjugate to both sides, we get that the adjugate of this product, Ni minus J times J plus L, it's the adjugate of NL. Okay. Now, the left-hand side is the adjugate of a product of two matrices, but it changes the order. So it's going to be adjugate of J plus L times adjugate of Ni minus J. So this equals the adjugate of NL. Okay. So let's write it on the next page. So we have that. Let me change the order. Adjugate of NL equals the adjugate of J plus L times the adjugate of Ni minus J. Okay. Now, what is the left-hand side? Left-hand side, so every entry of the matrix L is multiplied by n. And now when we calculate the adjugates, we're taking n minus 1 by n minus 1 determinants. So this will be n times n minus 1 times the adjugate of L. Now, the adjugate of J plus L we'll leave it as it is. And then the adjugate of Ni minus J, Ni minus J is the same thing as the Laplacian of the complete graph. Okay. And so in that situation, the adjugate is going to be the number of spanning trees of the complete graph times the all-in-one matrix, but the number of spanning trees of the complete graph by Cayley theorem is n times n minus to the power n minus 2 times the all-in-one matrix J. Okay, so we are at this point here, we have that the adjugate of L equals, well, n times the adjugate of L, if you simplify that n to the power n minus 2, equals adjugate of J plus L times J. Okay. Now this one equals n times the number of spanning trees of gamma times the all-in-one matrix equals the adjugate of J plus L times J. Okay. So now what we do, we want to get rid of this adjugate of J plus L. So what we do, we multiply this equation on the left by J plus L. Okay. Because we want to catch the adjugate of J plus L times the J plus L. So what do we end up with? We end up with n times the gamma. And now we have Lj plus J squared here. And on this other side, we will have L plus J times adjugate of J plus L. So we'll have a different order. This one is I use J plus L, so J plus L times adjugate of J plus L times J. Now n times tau of gamma, L times J was 0. So this one is 0n, and J squared was n times J. Okay. This one's the matrix times its adjugate is the determinant of J plus L times identity times J. Now we're almost there. What do we have? We have n from the first, from outside the bracket, and there's an n inside the bracket. So it's n squared times tau of gamma times the all-one matrix equals the determinant of J plus L times the all-one matrix, and therefore these numbers must be equal. So we get that n squared times tau of gamma equals the determinant of J plus L, and this is the same thing as tau of gamma equals the determinant of J plus L times n squared. Okay, I don't think this was done by Kirchhoff. I forget the name of the author, but yeah, this is a equivalent formulation of it comes from Kirchhoff Matrix-Tree theorem. Now we have this expression for tau of gamma as this determinant of the all-one matrix plus the Laplacian divided by n squared. Now the other, so we took care of the first formula here, and now let's do the second formula, which is the product of the eigenvalues of the Laplacian matrix. So we'd like to prove that tau of gamma equals mu2 times mu n divided by n. Good. So how do we do this one? Well, we use the hard work that we did so far when we prove that this fact. Okay. Now, here's the idea here. The matrix L has eigenvalues mu1 all the way up to mu n. The matrix J, what are its eigenvalues? Well, J is the all-one matrix, so it has rank 1. So 0 has multiplicity n minus 1, so I'll just put it here with an exponent, n minus 1, and the other eigenvalue is n, okay? So these are the eigenvalues of these two matrices. Now you have to be careful, just because two matrices have eigenvalues mu j and theta j, it doesn't mean that when you add up the matrices automatically you're going to get the sum of the eigenvalues. That works in some situations, and it works when the two matrices commute, and that's the case here. So we're a bit lucky because L times the all-one matrix equals the all-one matrix times L equals 0n. So these two matrices commute, L and J, so that implies that the eigenvalues of J plus L are the following. So they're going to be of the form right here. So they're going to be so mu1 corresponds to the all-one vector. So you have to be a bit careful. So mu1 corresponds to the mu1, which is 0 for us here, corresponds to the all-one vector, because you have L times the all-one vector gives us 0 times the all-one vector. And for the all-one matrix, if you multiply by the all-one vector, you get n times the all-one vector. So from here, we get that the first eigenvalue will be n plus 0. And then if you take something that is perpendicular to the all-one vector, so L, but if you take another eigenvector u, which corresponds to some eigenvalue mu j, let's say u, and this u is perpendicular to the all-one vector, because you can take an orthonormal basis of eigenvectors, say, then u is on, because u is perpendicular to the one vector, this is an eigenvector for j corresponding to eigenvalue 0. And from this equation, you're going to get that L plus j times u equals mu j times u. So the other two eigenvalues stay the same, mu2 all the way up to mu n. Okay. So these are the eigenvalues of j plus L. Okay. And now how does this finish the proof? Well, we look at the formula on the top and we plug the determinant is the product of eigenvalues. So we get n times mu2 times all the way up to mu n divided by n squared. And this gives us mu2 all the way up to mu n, the product divided by n. Okay, so we have proved this one. Now we will learn later how computing these eigenvalues, it's some techniques for determining the eigenvalues and so on. But so let me give you some simple applications. So let's say as a corollary, let's assume let gamma be a k-regular graph, like complete graph, cycles, Peterson graph, and so on, and denote by lambda1 greater or equal to lambda2. We change the order. We go from largest to smallest. The eigenvalues of the adjacency matrix. Okay. So different matrix. And then the following statements are true. The Laplacian matrix is equals k times the identity minus a. 2. The eigenvalues of L are the following eigenvalue are things that look like k minus lambda j for j between 1 and n. 3, the largest eigenvalue of A equals k, and its multiplicity equals the number of components. Okay. And 4, the number of spanning trees tau of gamma, which was before the product of the eigenvalues of the Laplacian divided by n, product of the largest n minus 1 eigenvalues, now can be written in an equivalent form as k minus lambda 2 all the way k minus lambda n divided by n. Okay. So this is in the first 3 parts, we just state some connections between the adjacency matrix and the Laplacian matrix of a regular graph. And in the 4th point, we specialize the formula that we found earlier for the number of spanning trees to this k-regular, to a k-regular graph. So proof, well, so remember that we show that L, the Laplacian matrix, its definition was D minus A, where D was the diagonal degree matrix of gamma, and A was the adjacency matrix which you remember, it's the V times V matrix. So the rows and columns are labeled by the vertices of the graph, where in the position A, I, and J, we put a 1 if I and J are adjacent, and we put a 0 otherwise. So this is a real and symmetric matrix because we're talking about undirected graphs. Now, if the graph is k-regular, that means the degree of each vertex x is k for any x. So that means that the degree diagonal matrix has k on the diagonal, so it's k times identity. And you plug it in here and you get k I n minus a. Now, the second part is easy because the matrix A and In commute. You can say K times In, but the eigenvalues of A, you know them, lambda 1, blah, 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 lambda n, and the eigenvalues of K times N are K all the way K. So therefore, the eigenvalues of Ki minus A, which is L, this matrix has eigenvalues K minus lambda 1 all the way K minus lambda L. Okay. Now the next part is that the largest eigenvalue is K. So first of all, if we take A and you multiply by the whole one vector, what do we get? Well, in the first row, you add up the number of edges that contain the vertex corresponding to that row. So that's going to be the degree of vertex 1. And you go all the way to the degree of vertex n. And because the graph is K regular, you get K, K, K. So it's K times the O1 vector. And because O1 vector is non-zero, in K is an eigenvalue of A. Now, to prove that K is the largest eigenvalue, you can go through the Laplacian. I mean, there is a proof which you can do directly. So let's do the proof directly. So okay. So lambda 1 is the largest eigenvalue, and I want to prove that lambda 1 is less than or equal than K. And if I do that, then because the fact of K is an eigenvalue, then these two facts together will imply that lambda 1 must be K. Okay. So how do I do that? Well, let's say, let U be an eigenvector for lambda 1. And I have A times this eigenvector U equals lambda 1 times U. Okay. Now this eigenvector U is, U1 all the way to UN. So it's a non-zero vector. So let's take one of its entries that is the largest. So let J be an element in N such that Uj is the maximum over all I between 1 and N of Ui. And then if I specialize this eigenvector identity to the row J, I get that AU on the row J equals lambda 1 entry J. The right-hand side stays the same, but the left-hand side is a summation over all, let's say, L adjacent to J of UL equals lambda 1. This here, lambda 1 times Uj. Okay. So now let me write here. So lambda 1 Uj equals summation over all the neighbors of J of UL. But Uj is the maximum eigenvector entry. So each of these ULs are going to be less than or equal than this Uj. Okay. So I'm summing up over all the neighbors of J, the entry Uj, and that's going to be K times Uj. And because Uj is the maximum, you can assume without loss of generality that Uj is positive. Because if it's not, you can flip you can just multiply the vector U by -1 and you get one in which the maximum entry is positive. So from there, and from this inequality, we get lambda 1 is less than or equal to K. Now, I leave you as an exercise to adapt this. You can adapt this proof to prove that in any graph, not necessarily regular, the largest eigenvalue lambda 1 in absolute value is at most delta gamma, which is the maximum degree. So you can just change the proof, replacing when you pick uj, you pick the one that has the maximum absolute value. And the same argument will work through to prove you just have to apply triangle inequality. And you can prove that lambda 1 in absolute value is at most delta, the maximum degree. So that's a more general result. Okay, so we proved 1, 2, and 3. Now, well, 3, we proved that the largest eigenvalue is k, so we did that, and its multiplicity equals the number of components. One can do a direct proof for it, but you can also use the previous work that we did. For the Laplacian, 0 is an eigenvalue of the Laplacian with multiplicity equal to the number of components of gamma. But now when you apply this result to gamma being k regular, in that case, L is the same thing as k times identity minus A. So 0, an eigenvalue of L, the eigenspace of 0 as an eigenvalue of L is the same thing as the eigenspace of k as an eigenvalue of A. And the multiplicity of 0, so this multiplicity of 0, it's the same thing as the multiplicity of k as an eigenvalue of A. So this is only in this case of regular graphs that you have this connection very close connection between the Laplacian and the adjacency matrix. If the graph is not regular, then that's not true. Okay. And now the last part 4, it follows from our previous result that it's the product of the Laplacian eigenvalues, and these Laplacian eigenvalues are k minus lambda 2 times k minus lambda n divided by n. All right, so quickly some consequences. You can get Cayley theorem as a consequence because Cayley theorem, the number of spanning, you're just counting the number of spanning trees of Kn. And it's a little bit of a circular argument because we used Cayley result in some of the previous proofs, but nevertheless, we can do this. You can, so tau of Kn equals this. So Kn is n minus 1 regular, and its adjacency matrix is n identity minus j, and it has eigenvalues n minus 1 with multiplicity 1, and the other ones are going to be minus 1 with multiplicities n minus 1, because n times identity gives you n, and jn gives you n, 0, 0, 0. Minus 1 and identity. No, yeah, I have a mistake here. This is not the n identity n. Okay, so okay, let's quickly go over. Oh, this is not the adjacency matrix. I'm sorry. This is a Laplacian matrix. So this is a Laplacian matrix. So the adjacency matrix, adjacency matrix for the, we have 0 on the diagonal, and we have 1 everywhere else. And so it's going to be j minus I. The Laplacian matrix, where we have n minus 1 on the diagonal, and we have a minus 1 everywhere else, this is going to be n identity minus j. And so here, j has eigenvalues n, and then 0, 0, 0. And I has eigenvalue 1, 1, 1, 1. So the eigenvalues here are going to be n minus 1 with multiplicity 1, and minus 1 with multiplicity n minus 1. Okay. And k equals n minus 1. And so by this previous result, we get k minus lambda 2, blah, blah, blah. So k minus lambda 2 will equal k minus lambda n, and it will be n minus 1, which will minus 1, which will equal n. So on the top, we get n times n minus 1 times, and you have an n at the bottom, so you get n to the power n minus 2. So that's a simple consequence. There are others, and we'll talk about them in next lecture.